Alright, another draft physics video production. Move this microphone a little closer. Alright, might help. So anyway, some more on the photon. And, jeez, the solar light is out. I have to fix that. I'll be back. It's always something. Alright, technology and such. Anyway, photons. Yeah, still on the subject of photons. And so I guess I'll preface with some basic arguments about how maybe you should think about scattering and different functions of photons, and contrast the two models and explain how their theory wasn't the best choice. You have to guess at what the function is based on what it produces. And you could say, well, they made some good guesses, but they weren't right. Okay, they needed to keep working on guessing on a better theory. And they basically said, no, we're satisfied with a pretty broken understanding. One that's overtly incomplete and has problems. The whole wave interference thing didn't make much sense, and then they found out about single photons going through the experiment, and the same results would end up coming out, and different things that didn't make much sense. And instead of starting over, saying, well, maybe we need a better theory of how this thing works, they just decided to double down and create bizarre notions of multiple universes and all kinds of other bizarre stuff to explain why photons are capable of doing all these mysterious things. And it's just, it's wrong. It's a mistake. And nobody will admit it, and they won't concede, and they'll just keep arguing and defending the religion. Religion was, it was an okay guess in an atmosphere of complete ignorance, but it's a lousy explanation in the context of knowledge and more experiments, and there's just no excuse for it anymore, frankly. So scatter would be the idea of photons are hitting something and changing direction. It's kind of a logical thing you could sort of understand. And as I've sort of argued, though, is this whole understanding of how things happen, like this hits this moves in this direction, and this moves off in this direction. And in traditional physics, the physics we deal with, bowling balls and such, this makes sense. But on the nuclear level, it lacks making sense, because we sort of know that there's little energy corpuscles, as Newton would call them, or at least friends of Newton would call them, they have a consistency, in the sense you can't kill this bit of energy. The quantum of quantum mechanics is sort of arguing that you can't really get rid of this. This thing has got an eternal life, and you can follow it through a system, and whatever you put in of this, you're going to get this out somewhere, and it's not going to be broken in some way. It's going to still be moving the speed of light. And that was one of the key things they discovered, was this whole thing, that all this stuff is moving the speed of light. And so you sort of have to understand that you can't have interactions where you break these things into pieces and part of the energy goes one way and part of the energy goes another way. And that really can't happen. What has to happen is more energy has to go in of quanta, the Q's, and yes, you can apportion them. You can have some number, 2 of the quanta go out this way, and then you can have 2 of the quanta sort of ride on this fellow and go this way. But you have to divide the quanta, the bits, have to do the function. And that you can watch a system of millions of these things, but you can't draw conclusions that because millions of them do something, like make a wave, okay, that you can make some assumption that the individual things are doing what the wave is doing. That the individual things can break into two and break into two. They can't. That's not how it works. It's not reasonable. And so when you think of the interactions, you have to kind of understand them as being these little things moving the speed of light, hitting something like an electron or a proton. Those are the solid existing elements of charge. And clearly charge means that they react quite differently. But I've already explained that part of 2 plus 2 plus 2 physics. But the key thing to sort of understand is that what really happens is this thing doesn't bounce off of this thing. This thing absorbs this thing and it gives back something else. So as if this electron was, it just held seats of its previous interactions with the universe, and it got a quanta came in this way, and it kept that one and gave back some other dopey quanta, and it's just making exchanges. So this energy basically becomes part of this thing, and it gives back something else. And that is how the universe functions, is through this absorption of this quanta. And in the process of doing that, this thing moves much slower than the speed of light. So if it absorbs the energy, it goes through time much slower. And that has huge consequences in terms of realizing that your wave, your force, your stuff doesn't get where it was going when it has to interact with this stuff in the same time that it should have gotten there if it reacted as you would like to think it reacts. Just all kinds of crap. Stop it. Anyway, all right. So scatter has to be understood in understanding this quantized photon. I mean, if they call it quantum mechanics, and they really don't take any account for it when they're talking about photons. So anyway, so you have to think, I think, to be reasonable, you have to kind of understand that the photon is not an elemental thing. It's an emergent thing. It's made of something. It's made of the quantas, okay? And that there's this concept of its polarization. That is, whatever a photon is, it does spread over a large area. And that the key ingredient is the fact that it has this frequency, that the thing that's happening, the quanta, is arriving at a frequency. And so scatter should be understood as if you're taking something that we're going from the very small, like scatter against an electron, to scatter against atoms, which are going to be thousands of times bigger. So I can't really draw that, but I could just say 10 to the, let's just make it the 9th for fun, bigger. And then you got another level bigger, okay, is where you're not interacting with electrons, but you're interacting with the atoms themselves, and you could do another 10 to the 5th or some other kind of big number size increase. So we're talking about how does this thing interact with things of all kinds of different sizes first, and that should be understood, that obviously the same basic function is going to look very different depending on what you're hitting. Something with atoms, well, I should have taken it one step further. It's not only just atoms, but then it's also interacting with clumps of atoms. So the subject of the video that I'll play is more about objects that are almost as big as the polarization of the light. So we're talking about something with multiple atoms now. What is something with a whole bunch, thousands of atoms interact? How does that interact with a photon? So we're talking about little thin pieces of crud, where you can imagine a thin piece of crud that, even though it's opaque, it wouldn't be opaque to a photon. Photons would be able to get through it. So if you make it thin enough, you can take a really thin piece of gold and you can see through it. And the same thing would be for little particles in the atmosphere, although they would be opaque particles, could be. They could also just be transparent ones, but yes, they could be opaque clumps. And those opaque clumps, like water blobs, little blobs of water, will interact with photons in a specific way. Then the argument would be is that for clumps of this small size, in the sense that it's not much bigger than the wavelength, the majority of the photons will go through the substance, vast majority, and a small percentage will reflect back. And the same is basically true for electrons and everything else. The motion is always in the direction of the energy, frankly, and that's just the way it's going to work. The energy is moving in a direction. Reflecting requires some opposing force if you're going to technically be able to create more energy in terms of reversing the energy, let's say. So, and it's only through exchange you can understand that you can exchange energy. I could exchange this bit for this bit going this way, and through that exchange process I've created a 2x increase in the overall motion or energy in the direction. I haven't made it go that way. I've either decelerated it by 2 times or I've accelerated it by 2 in that direction by just making that exchange. So in a sense it doesn't look conservative, but it clearly is. Okay, it just depends on you understanding that the real mechanism isn't some bouncing off of mechanism in the true sense of that. It's not in the common sense of it. You have to understand it in the nuclear sense of it. All right, so the idea would be is that there's the big thing is understanding, seeing this. People see this as a wave. Okay, so this frequency is a wave of stuff, and they're going to use a word like wave interference. And fundamental to this idea of wave interference is understanding essentially that it's really phase interference that you're talking about. So something starts off with a frequency, and what you do is, because it interacts with electrons and then gets readmitted through the same process, something jumps in this way, it moves, and then something jumps out. Okay, the thing that moved it, okay, ends up getting exchanged, and it jumps out, and now it goes back to being whatever it was before it made that exchange. So it loses this momentum, and it shoots a quanta in that direction. So what happens through these interactions is that the phase is changed. So this becomes this. All right. Now, if I'm in a wave, that is, I have a whole bunch of these guys going this way, right? They're all waving, and they're all doing the same thing, a bunch of soldiers all lined up, and now I start to unalign the soldiers. That is, I have a group of soldiers that's here, here, and here, start making a mess, okay, of the alignment. Well, now I'm losing my waveness. I'm losing my frequency detection, because now is the frequency this frequency, or is it this frequency, or is it this frequency? What's the frequency? So I'm losing something recognizable about the photon. So that's what's happening in this idea of scatter, is that little elements of this will interact with this. So you have a photon that's rather large, a piece of it, okay, because this isn't bigger than the photon, a piece of it interacts, and so this piece gets retarded in its progress. Now, any retardation is catastrophic. So if your mechanism, your machinery, is detecting this frequency, this is not going to be at all useful. It can't do 2 at once. It can't see both at once. It has to look for frequencies, and so it can't function. This becomes a lost bit. Now, it's not dead. The energy wasn't destroyed. It didn't hit this and die. It hit this, moved a little bit slow for a minute, okay, and then was readmitted back into the stream a little bit retarded, a little behind the wave front. So it's out of sequence, and that's all it is. So it's still there. It's still moving through space, okay? It didn't go some wrong place. And then the idea of scatter is that this is going to happen in different angles, but I don't want to confuse you too much. But anyway, the exchange in energy is going to be variable in terms of its direction, because this thing isn't going to move straight. All right, this thing has already got motion, and it's going to blend motions. It's going to make a composite motion in the end, and it's going to release energy in some other direction besides this one. It can release the quanta in some other direction, the frequency. It will release it in some other direction. And the point would be is that you're collecting more than one of those. So it happens in more than one place, and you end up making a new photon wave going a new direction. So the wave starts this way and ends up going this way. But it's going to be made out of these elements. So I retarded one element in this photon, and let's say I did send it this way. Well, another photon comes by, and another atom is retarding it, and it ends up putting it here. And then another atom does the same thing, and it puts one here. Well, now I'm reconstructing my wave again. I'm rebuilding the photon out of these pieces, these elements of other photons. So I'm making a new photon essentially, and I'm making one that has a different direction and a different, maybe even a different phase, out of the bits of quanta by merely adding a little bit of slowness by putting it in a boat for a while. Okay, and you know, the swimmer doesn't make the same progress when he's in the boat. So the swimmer's moving the speed of light in the ocean. He jumps in the boat and he becomes a rower. Yeah, he's going a lot slower. He's not making the same kind of progress. Okay, but he's got to share his progress with a bunch of other energy moving in other directions. So the boat ain't going to go where the swimmers individually are going. It's going to go where they're collectively going when they're rowing. So it's just a little bit of a change in an element of the photon. The photon isn't destroyed. It's just made unreceivable. And then you can reconstruct it. You can constructively reconstruct a photon. So there's no such thing as destructive interference. Nothing's ever destroyed. All you're doing is saying, can I put the pieces back together and recreate a photon? And yes, you can, because all you need to do is restore the phase and have a common direction that you're moving this stuff in. All right, take a little pause. All right, back. So the point, the takeaway from all of this is that you know, I just wanted to emphasize the point that photons are not. So when they say things like there's a 180-degree phase shift, all they're really saying is that's a destructive phase shift. That means you've moved the bit to a location that's dead in between the old wave. So your soldier is way out of alignment with the wave. And any out of alignment, they're just going to call it a 180-degree phase shift. So they'll say a surface is creating a 180-degree phase shift. It's not necessarily 180 degrees. We don't know how much time exactly was used up, and that's the phase shift. The phase shift is going to be how much time was spent moving electrons. And the time you spent being inside the boat, that's the part that's creating the phase out of alignment. And any out of alignment will just be called 180 degrees because it's always going to be, that photon is really broken now. I mean, it doesn't work. And you're going to have to get to 360. You got to get a full wavelength. You got to get from row 1 all the way to row 2 before we know you exist again. So they're just calling anything in here 180 degrees. Anything that's not 360 degrees is 180 degrees from their book because they're just saying it's broken. That's all. There's no automatic phase shift. There's always a specific amount. So a thin film, yeah, it doesn't matter if how thick your film is to some extent. In the sense, you can just say it's always a phase shift when you go through the material. Because when you're going through the material, you know, you're not reflecting. You're moving electrons, and so you're spending time in boats. But it doesn't matter how much time you spend. You could have spent just 10 minutes or 10 hours. If it's not going to get you all the way to row 2, it's going to be considered catastrophic, the end 180 degree. It might as well be right in the middle. So anything short is right in the middle to them. Their math will work because, yes, it's destroyed. In a sense, you're not going to receive it. You're not going to see it. And you're only going to see it if it gets back to this row again, because it's going to count as a real soldier again. It's like pushing the wall of the castle down. Everybody has to run at the same time and hit the wall at the same time, and then you can push the thing over. But if everybody's out of timing, you're not going to get anywhere. Pushing a car, lots of examples in the real world where, yeah, it just doesn't matter whether you're a little bit out of alignment or a lot out of alignment. Out of alignment is out of alignment. But nothing's destroyed. You're just saying there's no reconstruction. I can reconstruct, this bit with some other photon. I can reconstruct a photon if I have them on phase. I can't reconstruct it if they're out of phase. So I have to get them back in phase for them to be seen, for them to be a real photon again. So that's one of the dependencies. It's just a dependency that the phase be right. If they're out of phase, it ain't going to work. You're not going to see it. It's not going to be a rebuilt photon. So even if I have all the pieces, I put all the pieces back, if the alignment is wrong, there's one here and there's one here, and places that just aren't going to be able to make the front, the energy hit at the right frequency, then it's not going to be considered a photon. It's still there, but it just doesn't do anything. So all there is constructive reconstruction. All you can do is remake a photon after you broke it with a bunch of bits of crap in the way, and they all shot elements in a direction, and those elements can line up if the frequency is correct. If the phase is wrong, they won't line up. You're not going to make a new photon, and it doesn't matter whether it's a little bit off or a lot off. It's all the same off. Off is off, and that's all. And that explains all this wave interference stuff. You don't need any of this complex, wacky, wooey theory to explain what's happening. And all you have to really understand is that photons are emergent things. That's why they look wavy, is because they're a bunch of soldiers. And the bunch of soldiers, elements of those soldiers can be fractured off, and that you can essentially split the energy and have some of it go this way and some of it go that way, and you can remake a photon going one way and remake another photon going another way out of the energy of 10 photons that you put in the first place. And all you're really trying to follow is the change in speed created when you put swimmers into boats. It really is that simple. So, like I said, I can only reason with you. I can't force you to be reasonable. They have the wrong answer. Okay, and the right answer is, it has some similarities. It's recognizing their functionality, but it's explaining it rationally rather than irrationally. So, play the video.
Welcome to Lecture Online. In our quest to understand
poo. Ants. Yeah.
and photons better, we're going to talk about what we call me scattering. Now, in the previous video, we already looked at Rayleigh scattering, but now we're going to look at what we call me scattering. So what's the difference?
Well, let's understand. The difference is, okay, that in one respect, you're talking about how photons interact with electrons. Another respect, you're talking about how they might interact with whole atoms. Another respect, you're talking about how they react to whole clumps of atoms. And then you go probably one step further and say, yeah, what do they do when they hit a bowling ball? But that's the only difference. They're not, the concept isn't any different. You're just saying, well, yes, you're obviously more likely, the more electrons you put in the path of a photon, the more likely you are to create phase irregularities, changes in the timing of the photon, and the more likely you are to have specific reconstruction problems.
Well, there's three different regions of the ratio of particle size to photon size where we have different kinds of scattering. So the first type of scattering is what we call Rayleigh scattering. I have it right here. So Rayleigh scattering, and that occurs when the particle is less than 1/10 the size of the photon, or at least the wavelength of the photon, because the size of the photon is still something we need to tackle. It's a difficult concept, and it's really not we really don't think about the size of photon in the traditional way where we can actually put a limit to how big a photon is.
Well, yeah, no, we can. We don't have any problem defining the fact that it has this very specific polarization, a very specific length to its or size to its polarization. So it's not understanding it having a size that's the problem. It's understanding it as some thing, a solid thing that has a size. So it clearly is a composite. It's an emergent thing. It is made of soldiers. It's made of quanta. It's made of something. And they keep pretending it's just some kind of wave thing, and they don't understand that they have to account for the individual elements of the wave. And clearly, quantum mechanics is telling you, no, it doesn't do this. Okay, it's a clump at a frequency. And it's just hopeless.
But we're getting there. We're trying to understand what a photon is, and so we're going to look at it in terms of...
Okay, I'm saying that you're not trying to understand. You're just preaching out of a Bible. So you don't want to understand the facts. You don't want to collect the facts and make a good hypothesis and theorize in any kind of way. You're really not looking for the truth. You're just preaching one particular story, one particular explanation. And I would argue it's on its face archaic. It's a blend of stuff 300 years ago, Huygens, who you put on a pedestal and said, oh, this wave thing is so much fun. And so you want to retain a bunch of old ideas. You want to keep trying to shove them into the fact pool and say, we have a fact defending that theory, when you really don't have any facts. So it's just like an old archaic religion. It was a nice little story 2,000 years ago. It's a moronic story now, okay? And you don't keep putting moronic stories, moronic facts into your fact pool. You don't really have any evidence that anything is any kind of wave. You have all kinds of evidence demonstrating that waves are emergent properties, that oceans don't really wave, that the atoms, the molecules in the ocean are what are transferring pressure to each other. You understand that it's made of something. Waves are not elemental. They are not fundamental. They are not something in the physics in its elemental form. They are something that emerges out of the physics. And that physics, really, the whole point of physics is to get to the elemental function. So you're pretty much violating the rules of your own discipline. Why is it called physics? It's because the whole point is to get to the elemental function.
How photons are scattered in the atmosphere when they encounter particles in the atmosphere. So when the particles are really small, less than 1/10 of the wavelength of a photon, namely the air molecules in the atmosphere, then we experience what we call Rayleigh scattering.
So that diagram of Rayleigh scattering is, in my opinion, just overtly inaccurate. Most of the light does move forward. So he has drawings there of the proportions of the momentum that moves. So he's saying that with the bigger particles, more of the momentum is in the forward direction. No, it's also true for the small particles. Okay, the momentum is clearly in the forward direction. Most of the light gets through the atmosphere, even though you could argue that every single photon, that none of the photons went through and didn't hit any atoms. Okay, even though their atoms aren't really thick here in the atmosphere, there's still tons of them, and none of this energy that goes through this medium is getting a free ride. All of it's jumping in some boats. It's spending some time in boats. It's not spending nearly as much time as it would in glass or water, but it's still time. And it's still a fact that the energy goes that way. It goes the direction of the photon. The photons don't lose their direction. So Rayleigh scattering should have the same kind of diagram. Most of the energy goes that way, the way the photon's going.
It turns out that the amount of backscatter, or the amount of extinction, and so when we talk about how much of the light gets
all right, so let's understand. See, you said the word extinction. As I pointed out, nothing gets extinct. You never kill energy quanta. So if you understood that, you say, well, it has to go somewhere. And we know that the polarizing film doesn't melt. And we know lots of things don't happen. So we know the energy's got to still be there. It's just in a form where you can't utilize it the same way because your soldiers aren't in alignment. Okay, you can't knock down the castle wall because I run into the wall and then Joe runs into the wall and Fred's running into the wall. Everybody's running into the wall at not the same time. So our energy is not being constructively put to the task and the wall doesn't get knocked down. But if we all run at the wall at the same time, we can knock it down. It's that simple.
Scattered away or gets extinct or extinguished or absorbed in any way possible. So meaning how much of the light that is incident on the particles gets scattered back and gets extinguished, and how much of the light continues on forward. Well, we call that...
So again, there's no extinguishing. This is what the polarizing films demonstrate. You know, you put one this way, and then you stick the one this way in the middle, and you end up with more light. So here you are putting more filter in and you're getting more light out. It clearly demonstrates that their theory is wrong. Nothing got extinguished by the first filter. Nothing got extinguished by the second. Not nothing. A tiny percentage did die. But the truth is the bars, okay, were also transparent. And all the bars are doing is increasing the amount of out-of-phaseness. They're changing the out-of-phaseness. They're doubling it, essentially. So one film creates a certain amount of phase shift, the next film creates a doubling of that. And so all it's doing is changing the location of the soldiers in their out of alignment. And so you can always put them back in alignment by changing which part of the filter they go through, whether they go through the thick part or whether they go through the thin part. So all you're doing is saying, well, if I send Joe through this part, and then later I send Fred through this part, through a thick part, the two will now be back in phase, and they'll be able to knock a wall over.
The extinction coefficient, and that is typically a function of the ratio of the radius of the particle to the size of the photon. And so when it comes to Rayleigh scattering, when the particle is, let's say, less than 50 nanometers, because the wavelength of visible light is somewhere between 400 and 700 nanometers, so we take a tenth of that, or less than a tenth of that, we're talking about very small particles like air molecules. And so when the light is incident on that, in other words, photons of visible light, then a significant amount is scattered, and the amount of the scattering, the coefficient, or what I call the extinction coefficient, how much the light is scattered, is simply proportional to the radius of the particle divided by, that should be frequency, that should be wavelength. All right, there we go. So if the particles get bigger, the amount of light that gets scattered is bigger as well. So definitely a function of the size of the particle relative to the wavelength. But then as the particle gets bigger, and the particle now reaches a size somewhere...
He just said as the particle gets bigger, it reflects more, it interacts with more light. Duh. I mean, that's obvious, right?
Between 1/10 to a full wavelength in size. So let's say the diameter of the particle is roughly the size of a wavelength. Then we go into what we call Mie scattering. So what is different about Mie scattering?
So again, it's not the wavelength that's significant. It's the fact that the wavelength is the same as the distance of the polarization. The polarization depth is the same as the wavelength, or proportional to. So that's why it's significant in terms of your being affected by it. It's because now you're conceding that your ray of light has a thickness, and it's the thickness of the ray of light that is relevant in the scattering function.
Well, what it turns out is that the amount of scattering from the particle depends upon the direction. So let's say that the photons are incident in this direction, so that's the direction of the photons, and the photons are incident on the particle, which is now bigger than these very tiny particles, where we have Rayleigh scattering. Then more of the intensity of the scattering goes forward in a single dimension. For example, if the wavelengths, if the photons come in this direction, then most of the scattering will be in the forward direction, and very little scattering will be in the backward.
So again, and scattering is only being defined by something that you can detect, which is a misdirection, a change in direction. So the simple argument is the small particles, you don't see as much misdirection. The electron tends to move in the same direction as the energy. Whereas you get to a bigger particle, it already has its own momentum. And the exchange of the rower, the new rower, will mean a lot less because it's got to be divided over a bigger mass. So the trajectory the molecule was already on is going to have a more significant effect on the outcome direction. And so that's all you're saying. So really what's missing from that drawing is an understanding that in Rayleigh scattering, that the line in line with the photon is really long. There's lots of scattering in the same direction that the force was moving. Okay, so it's technically not changing direction, but it is going into the boat, it is getting its phase shift in, but it's moving in the forward direction. And that's what's really missing from this drawing, is that yes, the transmission is less likely to be broken into a direction. So this is really, when they say scattering in this circumstance of small particles, they're talking about transmission. They're talking about going through and being changed in your direction. When you get to big particles, we know they bounce off, they reflect. Like in a mirror or some other kind of object, we know some of the light reflects. It actually bounces off, which is fundamentally different from this transmission argument. So they're calling transmission scatter when that's really deflection. So in Rayleigh scattering, it's really not scattering, it's deflection. In the larger objects, yes, it can be scatter, But now we're talking about what's the motion of the element that the photon hit, and what it tends to move in the direction the photon's moving. Obviously, the change in direction when the photon interacts is likely to be in the same direction that the photon was moving.
Direction. Not only that, the amount of the reflection or the scattering in the backward direction depends upon the ratio of the radius of the particle divided by the frequency, but not just in a linear relationship, in a kind of trigonometric relationship like a cosine or sine function. It actually varies with that ratio, and then we can see that variation kind of diminishes as the ratio of R.
All right, so now he's trying to combine two things and call them one thing. So this gets a little bit complicated, but anyway, I'll try to explain it in the simplest terms. There's two variables you're considering. You're considering the size, the variability of where these photons, the distance they're traveling. Okay, so that's your wavelength or your polarization depth, and then the size of the particle. So there's two things you can vary. You can make this bigger and smaller and leave this the same size, or you can leave this the same size and say, well, what does it look like when it hits a particle this big? And what's it look like when it hits a particle this big? So if I was to chart the two things, changing the two variables, right? So you could say, leave this a constant and try this, A, B, and C, right? And if I do A, B, and C, you could sort of see that obviously there's going to be more scatter for this size wavelength depending on which one of these I choose. A, B, or C is going to have a very different effect. I mean, A is only going to affect one little piece, B is going to affect 4 or 5 pieces, and C could affect the entire photon, could end up being absorbed and re-emitted. So they're obviously going to have very different effects. So if you were putting that on a chart, the chart could look something like this, right? Because you're charting the effect of changing the size. Well, now if I put on the same chart, well, what if I leave this the same size? So I just go with B, okay? But now I change this wave into something much bigger, okay? And now I say, what happens when this wave hits B, and then a smaller wave hits B, and a smaller, what happens when I take this wave, and then, all the variable sizes of wave. Oh yeah, I got a chart that looks like this, and so he's going to make he's going to do exactly the opposite. He's going to make something like this and say this is how it charts. Well, that's because he's charting two variables at the same time. He's changing two variables, and so that's why the chart looks like that. So, but all you're really saying is what's the difference? The only thing that really matters is the thing that's going to make the chart go like this is the fact that the only thing that matters is what's the proportion. Is this half the size of this? Or is this the same size? And that's all that's changing. So you're just basically saying the bigger you make the particle, the less scatter that you're going to get because you're really dealing with whole photons then. The whole photon can hit the object when you make it big enough. So I'm just trying to give context to what he's going to say and to understand that there's nothing truly changing. You're just changing two different variables at the same time and then charting it. If you do that, your chart's going to look pretty silly.
It gets bigger. So therefore we have an e to the minus k r over f term. I'll put that in quotation marks because that's something that I kind of came up with to kind of give a feel for that. So the amount of scattering will depend upon some sinusoidal function that seems to diminish as the r over f gets bigger. And so we kind of have these type of components related to the amount of scattering experienced in scattering. But you can see that there's some scattering in the back.
So all he's basically saying again is that as you change this relationship between the size of the particle and the frequency, they're two separate variables, and yes, if the frequency is the same size as the particle, then you get very little, and if it's the frequency, and if the polarization is many times bigger than the size of the particle, then you're on those high lines, the big change.
Backwards and down direction, and the predominant scattering in scattering is the forward direction. As the particle gets bigger, you can see here the particle is bigger again. As the particle gets to be about the size of the wavelength or bigger than the wavelength, then more the direction of the scattering is forward in the same direction as the approaching photon. And you can see that very little of the scattering goes backwards. At some point, the coefficient of the
So another way to understand this is they're calling transmission the same thing as scatter. So in one case they acknowledge transmission, and in the other case they're not. So in this case they're acknowledging transmission as a form of scatter. In the first case, Rayleigh, they're not acknowledging transmission, pure accurate transmission, as part of the equation when it should have been.
Extinction coefficient becomes a constant. So it's regardless.
All of them create motion in the forward direction. That's just energy conservation. All of them scatter in the forward direction more than in the reverse direction. There technically is no reverse direction in the sense that the matter itself will be moved forward. The energy is real and has a real consequence in one direction, and it's only aberrant elements of the energy that can be going against the flow, and those aberrants were something already in the matter. The electron already has to be moving in a direction for there to be a reflection in the opposite direction. You have to be slowing an electron down going the opposite way to create scatter in the opposite direction.
Of the size of the particle relative to the wavelength, the scattering then becomes uniform in the direction proportional to the intensity of the light, and so therefore we then have what we call optical scattering rather than Mie scattering. So the Mie scattering then becomes the type of what we call optical.
I really like these drawings just because they sort of illustrate my point, which is the fact that as something moves, the interaction you're going to have with it also changes, in the sense that it's harder to add energy to something that's already moving the same direction you're moving. It's hard to push something moving, effectively. Just like it's hard to throw a fastball, okay, from a moving train, okay, off the back of the moving train. Because to throw a 90-mile-an-hour fastball, for a catcher to be sitting there saying, okay, hit me with a baseball going 90 miles an hour. Well, if I'm doing it from the back of a train moving 90 miles an hour, I have to throw the baseball 180 miles an hour. I can't add energy to that glove, okay, without adding a lot more energy than it would take if I wasn't moving 90 miles an hour away.
Scattering, the light simply scatters off a large particle. So Mie scattering is kind of the scattering that we find in the in-between stage. Between Rayleigh scattering and optical scattering, we have what we call Mie scattering, and the scattering is kind of a very interesting way in which it's done. You can see then that the amount of light that gets scattered forward and backwards depend upon the ratio.
Okay, so again, he's, especially because it's the middle term, he's just overtly not acknowledging that some of the scattering is just transmission. It's not bouncing off, it's transmitting in a new direction. And so it's technically, I would argue, not scattering off the particle. It's not bouncing off the particle. It's being absorbed by the particle and then retransmitted by the particle in a new direction. And they're not acknowledging that transmission and scatter are essentially the same thing. And you always have to include transmission with any argument about what scattering is doing, or you're kind of missing half the story.
Of the size of the particle to the frequency, and you can see that this is roughly from 1/10 the ratio of R over F. Oh, I keep saying F, but I want to say lambda. So we go from about 1/10 the ratio of the radius of the particle to the wavelength of the particle to about 1 times the ratio of the radius to the wavelength. So in this region, when the particle is roughly...
So again, I just argue that that's charting poorly, because what that chart isn't telling you is that first I'm varying the frequency, and then I vary the size of the particle, and then I vary the frequency, and then I vary the size of the particle. The chart doesn't really have anything to do with doing what you have to do to chart something, which is have one variable in a group of constants, not two variables in one constant.
1/10 the size of the wavelength to about the same size of the wavelength. In that region, the scattering will vary kind of like sinusoidally, and the difference here in the beginning especially is basically a 10-to-1 ratio. So it's quite a dramatic change in the scattering as that ratio changes from 1/10 of R over lambda to 1 times R over lambda.
Right, so it's not changing the scattering. So so again, you could eliminate that crooked line by just recognizing that all the crooked line is really telling you is how much is transmitted versus how much is scattered. Another way of looking at it.
And then, of course, it also diminishes like this. And so that's why I kind of threw this in there. So we have a declining exponential function. So as r over f gets bigger, then the variation in the scattering gets smaller. That's kind of an interesting relationship. So that's what we mean by Mie scattering. Notice it's in all directions, but the forward direction, in the same direction as the approaching photon, is where the predominant light will continue to scatter, and a little bit will then get backscatter. Of course, the amount of backscatter does depend upon that ratio.
And at these sizes, again, till you get way past optical scatter, this is really a conversation about transmission and about how much the material affects the direction of the transmission. And as I pointed out, obviously, affecting an electron, a small thing with your photon, you're going to keep the momentum in a more consistent direction than when you start hitting larger and larger objects. The larger objects already have a motion, and their motion is going to be combined, and so the scatter is just a combining of the pre-existing motion of the atom combining with a new rower you're adding, and then you're going to release the new rower from the combined direction, and that's where the new energy, the rower is going to start swimming in that direction. Where he was swimming this way, he's going to start swimming this way when he's released, because it's going to be mixed with the motion of the boat.
Now, where do we see that in nature? Well, when you look at the sun, especially in the sun when it's kind of a hazy day, where there's a lot of moisture in the air, a lot of small dust particles in the air, then you look in the sun direction and you can see around it kind of a halo of white light. That halo of white light is really a result of the Mie scattering that then hits those particles of that particular size. If the air is very clean, then you don't see that Mie scattering. Then, of course, we just see typically just a Rayleigh scattering if the air is pretty well fluid.
Well, like I say, you really don't see the scattering. You just see photons coming from the wrong place because the light is diffusing. It's spreading over all kinds of areas, and it's hitting other things and bouncing back to you from places it didn't start off from. So it starts coming at me from this direction, and it goes this way and hits something over here, and then it goes over here, and then it goes over there, and then it gets to me from this thing. So I think it's coming from that direction when now it came from this direction, and it took a very long path to get to me, and it had to be rebuilt to get to me. More than one photon, the elements of more than one photon is the only time this scattering is going to happen. You have to throw more than one photon at the system. So if they could do the single photon experiment, they would see that scattering doesn't even happen, because the photons are not going to be made out of the one original photon. It's going to be a rebuilding of your army men. Your army men get out of phase, and what you do essentially is they go in different directions, and you're lucky in the sense that you send 6 of them in the right direction who have had the same experience. That's, they took the same amount of time to eat lunch, and so they get back in alignment, and so you create a new photon. But that's what's really happening. That's a better theory.
Free of the moisture, kind of like the fog particles or kind of like dust particles in the air. Another thing is, for example, when you turn on the beam of your car, the headlights of your car, in a foggy condition, then again you see what we call the Mie scattering, where we have this back scattering, and that's why you don't recommend.
Yeah, the irony is, though, is that what you also recognize is less of your lights going forward. So much of it is getting bouncing off the big giant water molecules, very heavy ones. And you're getting a ton of reflection. So it's not even consistent with his drawing, in the sense that really a large percentage of the light does end up being diffused and sent in the wrong direction. So it's counter to what he's arguing, almost. Counter to the drawing.
On high beams in foggy days, because you get much of that light reflected back in your eyes and they can't see anything. So hopefully that gives you a good idea of what Mie scattering is. And again, it relates the properties of photons to what happens in the atmosphere when it encounters different sized particles and the different kind of scattering that the light then experiences.
I mean, you can just theoretically, you can understand that the more fog I add, like the more milk I add to water, the less transparent it gets. So I put a little bit of milk in the water, it diffuses the light, and light comes from all kinds of places. But the more milk I put in, eventually I don't get anything coming out anymore. I mean, it just kills my light. entirely. It absorbs it all into internal reflections and whatnot. And the photons get so broken that I won't see any of them coming out, and all we have is, infrared radiation or some radiation that's formed by the molecular movement and nothing else.
Also, of course, when we have this kind of a variation, depending upon the size of the radius of the particle versus the wavelength of the photons coming in, then we have what we call kind of a diffraction result, because then we have some sort of interference of the scattered light.
Right, so there's no interference, there's just constructive reconstruction. You either put photons back in phase, in alignment, or you don't. That's it. There's no destructive. There's either put it back together or leave it broken. Put it back together, leave it broken. That's it. Nothing else. Nothing is destroyed. Nothing destroys.
Which then causes these variations in the intensity of the backscatter. And we'll get into that a little bit more as we continue looking at these videos to try and understand what photons are.
Like I said, you're not trying. You're not trying nearly hard enough. Okay? All you're trying to do is rationalize silly theories like bent space and whatever, wooey mechanics. And that's it. You're just defending an ideology. You might as well put your robe on and your silly hat and a little smoking urn and just say, believe what we say, believe it. Even though we really haven't thought about it very hard. We never went back to the beginning and looked at the bones and the evidence. And so, yes, it was a dinosaur. It wasn't a dragon. We understand now. Oh, it was a gorilla skeleton. It wasn't Goliath. We never cared to really inspect why we're believing this silly crap. Okay, that's cobbled together over 300 years, piece by piece, just piled on clay on top of clay, and you made a mess, and you don't want to go back and start over and do it right. It's the truth. All right, so enough said, I think. So, all I can do is attempt to reason with you. I can't make you reasonable.